Okay, 5B. So we're going to talk about current voltage dividers, doing power calculations, RMS calculations, peak envelope power, and decibels, and time constants, and more phase relationships, RT time constant, the phase angle in reactive circuits, we talked about a little bit, and more admittance and susceptance. I don't know who comes up with the questions for the pool, but anybody can suggest something, and then the INVEC either adds it or not.
Can we suggest that they take things out?
Yeah, yeah. And they do occasionally, or reword them. Okay. There's a thing called Kirchhoff's law. If you remember that, and there's actually two laws, his current law and his voltage law. And they work most of the time, except when there's magnetic fields involved, which we won't go into, but they behave different. In the case of the current law, it says that the sum of the currents in and out of a node, you've got components connected, add up to 0. So the current in will be equal to the current out. So you got a plus in, you got minus out. The sum, if you do it around the node, will be 0. His voltage law is very similar in that in a parallel circuit, a loop, the voltages around that loop, because the currents can be different, will add up to 0. And it's a fairly simple loss. So if we remember that the total I into the node is going to be equal to the voltage at that node divided by the effective or the total resistance. So in a parallel resistive circuit, okay, we've got E divided by R1 plus E divided by R2 plus R3 plus however many there are. Okay, and that will give you what a little thing there, that total current. So we have an example circuit here where it's got both nodes and loops. So in the case of the node, you've got the current coming through R1 into this node, and then you've got a current through R2 and through R3, and those R2 and R3 currents are going to be equal to the current through R1. In the case of this loop, we've got a voltage across R5, R6, R7, which are in this direction, and a voltage across R4, which is positive. So if you add those up, as these plus and this minus, you'll get 0. And I can't tell you how many damn circuits we had to do this way in college. That was a big thing. This is just another one showing the currents in and out of the node, the voltages around the loop. Another actually worked out example where we have 14 milliamps coming out of the battery and how it's distributed through the 3 currents through the 3 resistors because they're not equal. So how does the total current relate to the individual currents in a circuit of parallel resistors? In other words, what does Kirchhoff's current law say? Charlotte? Okay. RMS. Everybody know what RMS is? Well, it's easy to say. What is it? It's the square root of the means squared. So essentially what they're doing, if you look at this little sine wave diagram, and you see the dotted line, which is what the RMS value is, they're basically flipping the negative cycle up. That's what happens when you do the square under the square root. You make them both positive. And then you clip the top off enough to fill in these voids. So you get the effective DC value of that AC wave. So the definition is for RMS, it will dissipate the same amount of power in a resistor as a DC of the same voltage. So that's all they're doing is coming up with an equivalent DC voltage. And it works right well if you've got a nice sine wave. If you've got a nasty sine wave, the formula doesn't work that well. And most of your meters don't, unless you get a true RMS meter. And even some of those, I'm not sure are really true RMS.
And the scope is very difficult also if you get it right.
Yeah. So the way you calculate is, well, they have a power average, okay, which is equal to RMS, the RMS voltage squared divided by the resistance, or the RMS current squared times the resistance. So the example there is if you had 1 volt RMS into a 1 ohm resistor, you're going to dissipate 1 watt. Likewise, if you had 1 volt DC, you're going to dissipate 1 watt. So when we look at peak voltage on the AC waveform, which is 0 to a positive or a negative peak, okay, it's going to be the square root of 2 times the RMS voltage. Or the opposite is the RMS is going to be 1 over the square root of 2 times the peak, or 0.707 times the peak. If we have peak to peak, we have to divide by 2 to get the peak, and then do the other one. Any questions on those?
Yeah, right, though.
Maybe not.
To peak, you need to divide it by 2 and then divide that all by square root of 2. Well, the math works out.
I think it's right. So what value an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value? Charlie. That was a gimme.
Yeah. Even I got that.
But that's on the general. What's the RMS voltage of a sine wave with a value of 17 volts peak? Well, you can throw Charlie and Delta away, right? It can't be higher.
Yeah, that'd be a miracle.
So it was 0.707 of 17, 12, or 8.5. Very good. What's the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? This is what you actually see in your wall socket. Even though they call it 120, it's a lot higher than that.
Yeah. No, it's 170.
times
Oh.
two, okay.
Times two.
Pretty high voltage.
Yep.
Okay, so power calculations. Power is the rate at which energy is used or consumed. We normally measure it in joules, named after this guy, Joule. All these things were named after old dead scientists, or engineers, or whatever. We have a nice little chart there, the pie chart. If you know how to use the pie chart, there you put your finger over the one you want. And so if we want power, we multiply the current times the voltage. If we want current, we divide the power by the voltage. If we want voltage, we divide the power by the current. And Joule's law is power is I squared, the current squared, times the resistance. And this is for purely resistive circuits. It gets more complicated when you throw reactants in. And there's just the Ohm's law formulas. So I went through the algebra down here to derive all that stuff, and you come up with the E is equal to the square root of power times resistance, or I is equal to the square root of power divided by resistance.
Indian, the eagle, and the rabbit. The Indian, the eagle, and the rabbit.
Okay.
What's that?
I hadn't heard that
I'm
one.
old.
Well, I am too, but I still haven't heard
The
that.
Indian, the eagle, and the rabbit. Eagle's always over the Indian, right? Eagle's always also over the rabbit.
He's talking about the Ohm's law pie chart.
Yeah, not this.
EIR.
So you can remember.
Like Eli the Iceman is one of those.
Yeah, okay.
I hadn't heard that one though.
That's from about 60 years ago.
Well, I'm not old. That would have been college. How many watts of electrical power are consumed if 400 volts DC is supplied to an 80 ohm load? 80 grand. So we've got 400 volts and an 80 ohm, 800 ohm load. So it's what? E squared divided, right? Not bad. You did it without a calculator.
I get it. Oh, wow.
That's what you learn about.
How many watts of electrical power consumed by a 12 volt DC light bulb drawing 0.2 amperes? This is an easy one because for general.
Ain't gonna be very much.
That must be an LED bulb.
A little bit.
How many watts are consumed when a current of 7 milliamps flows through a 1,250 ohm resistor? Now you can get a precision one
You
then.
get the precision ones, but they cost a lot of money.
Oops. Not on surface mount. They're dirt cheap.
I gotta have a class on the computer.
The calculators can be a problem.
If you think this was a problem, I'll bring another one and show you.
Yeah, I missed a question on my extra because I forgot my calculator and they gave me a loaner and it worked totally different.
Oh, yeah.
And there was this one problem that I had worked many times and I could not, but I didn't try to remember the answer because I knew I could work it. I finally gave up.
Well, you can bring your own alpha.
Alpha?
Yeah.
You think it's alpha?
I do.
Okay.
I'm positive.
Anybody else think it's alpha?
I think so.
Alpha.
Using my. I can see this.
It's alpha. You're on a roll. What's the RMS voltage? Across a 50 ohm dummy load dissipating 1200 watts. You got your linear cranked up to 1200. What's the voltage out there?
Bravo.
We got a Bravo. Any other guesses?
That's really big. Yes. It's bigger.
Bravo is right.
Oh,
The RMS was a red herring because it's the same as the DC, and we're doing DC. Sometimes they throw those tricky things in. Okay, peak envelope power. This is confusing to a lot of people. I get confused with it too, but I think I have it straight. Because there's different definitions that I think some of them are wrong. But in peak envelope power, it is the peak of the envelope of the waveform, like they're showing right here. In this modulated waveform, that those highest values of the modulation envelope is the peak envelope power. If you have an AM signal with no modulation, all you got is the carrier, then the peak envelope power is the average power. It's just whatever the carrier power is. With single sideband, if you're not modulating, you have nothing. Or you're supposed to have nothing. So again, the peak to peak is going to be twice whatever the peak is. Vice versa, the peak is half of the peak to peak. The RMS value is the peak times is 1 over the square root of 2, or 0.707 times the peak. And then if you're doing peak to peak, you got to divide it by 2 and then do the 0.707. So let's see what's down there. Anything important? Oh. So they're saying the peak envelope power is going to be the RMS voltage squared divided by R. Oh, these charts are all on Dropbox. I think I gave you a link. So what is the ratio of peak envelope power to average power for an unmodulated carrier. It's not a trick question. Bravo? Bravo. What's the output peak envelope power of an unmodulated carrier if the average power is 1,060 watts? Bravo?
Yep,
Bravo.
modulation.
What's the peak envelope power produced by 200 volts peak to peak across a 50 ohm dummy load? So that would be 100 volts peak or 70.7 volts RMS. Very familiar number because it's your typical transmitter.
I'm gonna say it's 100 watts.
Did you get that?
Well, you threw in the 50 ohm dummy load, and we haven't talked about resistance anywhere about, I don't recall.
Well, we did power. What's power? When you have
E squared.
when you have voltage and resistance, it's E squared over R, right? And the E squared in this case is R. We want RMS.
Say that again?
We want RMS
Yeah.
voltage. So 70.7, which is what this come out to be, squared, divided by 50, is approximately 100 watts.
Damn, this ain't nothing but damn math. Nothing but math.
Hey, Harold, your microphone's unmuted.
Okay, well, that one's not on the extra.
Well, then I'll forget about it. Already.
But you gotta know how to do it. So what's the output peak envelope power of 500 volts peak to peak across a 50 ohm load? So same question, they just changing voltage.
You know.
So again, it would be what? Peak is 250. 0.707 times 250 is, I don't know, something, 100 and something. Square it, divide by 50. Get a lot more watts. Yeah. Okay, decibels. Everybody knows decibels, right? 3 dB is 2 times or half, depending on whether it's plus or minus. The formula is 10 times the log power, log base 10 of the ratio of something. And we usually say if we're doing it in milliwatts, then we use dBm. If we're doing in for antennas, we do dBi for isotropic radiator. dBd if it's a dipole, relative to a dipole. 6 dB is times 4, 10 dB is times 10, 13 dB would be how much? How many times? 20?
Man, you just rattled that off.
Well, you ought to be familiar with them.
15 dB.
15 dB is going to be a little less than 40. If it was 16 dB, it'd be 40. They add. So 10 and 3 is 10 times 2. 10 and 6 is 10 times 4. 10 and 10 is 20 dB, which is 40.
Proceed. I'm going to have to do some studying again. Been a long time.
Okay, or 20, I shouldn't say 40.
I will remember.
The one important one here is how to do the anti-log. Okay, so if you, and because there's a question, I'm pretty sure it's on the general. It's probably the hardest question on the general, which I think is coming up next. And you have to do the anti-log. So the way you do that is you take the exponent, figure out what the ratio, what the log is, and raise it to the power of 10, divided by 10, because the log or the dB is 10 times the log. So you've got to divide the log by 10, and you raise 10 to that power, and you get the anti-log. In other words, what was in that ratio of P1 to P2 or whatever you're doing. It might be clearer when we get there. So what dB change represents a factor of 2 increase or decrease in power. 3 dB. It actually comes out 301. This is the hard one. What percentage of power loss is equivalent to a loss of 1 dB? So what percentage of power, percentage-wise, do you lose if you have a 1 dB loss, which is fairly typical in your transmission line? Even a couple connectors. 12%. This is where you need to do the anti-log to calculate it. But if you just want to remember the answer because it's an interesting one, it's surprising how much it is, 20%, almost 21%. You think 1 dB, that's not much.
If it's a lot.
But it's a highly non-linear curve.
True, but still, you're losing 20%.
But if it was 3 dB, you'd be
Half, 50%.
Damn, how come you can't move that damn thing?
a third there, 50%.
No, didn't work that way.
It's not linear. It's not linear until.
They'd ought to be.
But anyway, there's how you work it. You've got to do the anti-log to do that. Okay, time constants. If you have RC circuits, okay, where you're a series RC where you're charging a capacitor through a resistor, it takes time to charge it up. And we measure that in time constants. We use the Greek symbol tau to represent a time constant. And it's the product of the resistance and the capacitance. One time constant will charge up to 63.2%, or if you want to think it approximately 5/8 of the value, or discharge to 36.8. Two time constants will get you 86.5 or discharge to 13.5. And 3 time constants will get you up to 95% or discharge to 5%. So we normally talk about, use the 3 time constant thing to get close to full charge or dissipate the charge. The actual formula plotted is this start the voltage times 1 minus epsilon to the minus t over tau. And you actually, if you do that, you can get a plot like that. It's much easier to have the computer do it. But that's the kind of curve you get when you apply a square wave to a capacitor, an RC circuit, and then when the square wave goes away, it discharges.
What were the axes on that chart? Time and
Time on the bottom
yeah.
and voltage on the vertical.
Oh, okay.
So it was 1 volt, 1 volt square wave. That was, let's see, started about 40 milliseconds and went to 120 something. I don't remember what frequency I used. I played with it to get a nice curve. What's the term for the time required for the capacitor in an RC circuit to be charged to 63.2% of the applied voltage or discharged to 36.8 of the initial voltage? 1 time constant. What's the time constant of a circuit having 2 220 microfarad capacitors and 2 1 megohm resistors? And they say all in parallel, but they mean the 2 capacitors are parallel and 2 resistors are parallel, but they're in series. In other words, you got 2 resistors and 2 capacitors. So effectively, the capacitance is, with 2 220s in parallel, 440, right? And you got 2 megohm resistors in parallel, so you got half a megohm. So half a megohm times 440 microfarads with your calculator, and you get one of those answers. 220.
Now, you got the 2 capacitors in parallel and 2 resistors in parallel, and those
They're in series.
no, they're in series.
In series.
So that's changes the word series.
I know.
Yeah,
It's very confusing, but I didn't write it.
Series parallel.
So it's just the, standard time constant formula. More about phase. We talked about Eli the Iceman. Here it is again. I didn't learn about that in college. We never used that. So the voltage in an inductor leads the current. The current in a capacitor leads the voltage. And this is just the way they work. It's the laws of physics. And the reason is you're getting that either positive or negative phase shift, depending on whether it's an inductor or a capacitor. So what's the relationship between the AC current through a capacitor and the voltage across the capacitor? So the relationship between the voltage and current and a capacitor. What'd you say? Delta?
Is it always 90%?
Iceman.
Is it always 90%?
In the capacitor, Now, if you got resistor in series, then the resultant phase is less because it's going to be whatever that angle is. But you plot the reactance vertically because it's 90 degrees. The capacitor down. Same thing for an inductor. Okay, we're going to do Eli instead of the Iceman. So the voltage is going to lead the current. So we see the voltage rising prior to the current rising. So if you look at these peaks, if I had a scale there, you'd see that they were 90 degrees or pi over 2 radians apart.
So that phase delta is the amount of time it takes to generate the magnetic field in the inductor. That phase difference between voltage and current is the amount of time it takes to generate the magnetic field in the inductor?
Yes.
Okay.
Because that's what you're doing, is
For capacitors, it's the other way around.
right, you're filling up,
Charging.
you're putting a lot of coulombs in the capacitor.
Right.
And you're putting a lot of whatever we call them in the inductor.
Yeah. That's cool. So the two losses were
It takes the coulombs to generate the magnetic field, but you're storing the magnetic field as long as the coulombs are flowing. Which is why they work different, where the capacitor will hold it, okay? Even if you take the voltage away, if there's no way for it to discharge, it'll maintain the voltage. The inductor requires current flow. And as soon as the current increases or decreases, it changes the magnetic field. In fact, Dan, would you go to the car again?
Sure would be.
On the driver's side rear is my lens law demo. You know,
Is that the
plastic and copper pipe.
Yeah.
What's the relationship between the AC current through an inductor and the voltage across an inductor? Voltage leads current by 90 degrees.
Old Eli?
Huh?
Old Eli.
Old Eli. Okay, now we've got a series RLC circuit. So we have resistance, capacitive reactance, inductive reactance. So they all add up. So we get the real part plus the result of the imaginary part, which is the difference between them. So if it's negative, it's capacitive. If it's positive, it's inductive. And we get a vector because we plot the real part along the x-axis and the imaginary or reactive part along the y-axis. And we usually plot it like that. So the magnitude of the impedance, which is the length of that vector, okay, which is Pythagorean's theorem, sum of the square root of the sides. And whatever that angle is the resultant phase angle. So when you put the resistor in there, you no longer have a 90-degree phase shift for the circuit. The component itself is still 90 degrees, but with the resistor in there, it's going to change the phase angle.
With a resistance of 0, that'd be 45.
No, it'd be 90 degrees.
Or 9?
Yeah.
Oh, that's, yeah.
Because you have nothing on the x-axis.
Okay.
And that angle is going to be the arctangent of the reactance divided by the resistance.
So what do you, when you have a 45-degree angle,
Yeah.
you've got some resistance component.
Right.
And half, they're equal. The resistance and the reactance are equal.
Okay. But nothing important about
Nothing
that.
special.
No.
Okay.
It's just that in your house, when you have that, you're paying for a lot more power than you're actually getting. We'll talk about that a little bit. Because you're going to have some apparent power versus real power. And the real power is what's dissipated. The apparent power is what's happening in the inductance and capacitance, and it doesn't dissipate any energy, but it can draw more current from the power company. And they charge you based on how much current you draw. They don't care about your phase angle. There was a NASA guy years ago that invented this little gadget you could put on your power entry box to correct for the power factor. So you didn't get charged for that extra current. I don't know if it worked or not, but he's made a lot of them. Okay, so the phase shift is the phase angle between the voltage across and the current through that RLC circuit. So what is the phase angle if the inductive reactance is 1,000 ohms, R is 1 kiloohm, and the inductive reactance is 500. So we want to find the phase angle, so we take the arctangent of the reactance divided by the resistance. The reactance is the difference between the 500 and the minus 1,000. So it would be minus 500 divided by 1,000, or minus 0.5. So the arctangent of minus 0.5 comes out to minus 26.565 degrees. Because it's negative, we know it's capacitive. So we say the voltage is lagging the current.
Why didn't you subtract the 1,000 ohms, 500 from 1,000 instead? I mean, could you have done it either way there? Upper part of the fraction.
Say that again?
You have 500 minus 1,000.
Right.
Why couldn't it have been 1,000 minus 500?
Because 1,000 is the capacitive reactance, it's negative.
Oh, it's the capacitance.
I dropped the J's.
Okay.
It's really J500 and minus J1000. Because they don't, in this calculation, they don't matter. Because you're looking at the magnitude. So let's calculate one. What's the phase angle between the voltage across, current through, if capacitive reactance is 500, R is 1 kiloohm, inductive reactance is 250. So we already see that it's going to be capacitive because I have a higher negative than I do a positive.
If all I can do in our brains and understand.
Yeah, sometimes you have to do a secondary function to get arctangent.
Yeah, that's hyperbolic.
No, you don't want hyperbolic.
Oh, I know. It doesn't happen.
Okay.
But with our
If you get that question, you'll need a calculator. And unfortunately, you're not allowed to use your smartphone.
Which is good because they didn't have that. But so you can bring your own calculator. It's not like.
Well, it should. You should have a scientific.
Oh yeah, but just have to.
Well, if you do tangent, there may be a second function that will give you the arc tangent, an arc sine, and arc cosine.
And that's good. Windows calculator.
These things are $10.
I have one.
Yeah.
It's sitting at home.
It takes $1 million to learn how to use it.
So 14 degrees. So we're gonna do the arctan of minus 250 divided by 1,000, so it's minus 14 degrees. And it's capacity.
It was like,
Yeah.
What's the phase angle between the voltage and current if capacitive reactance is 300, R is 100, and inductive reactance is 100? There's a number of these, so there's a good chance you get one on the test.
60 by 63 by 8.
So 63 degrees, and we're still capacitive because it's negative. So let's try 25 ohm capacitive reactance, 100 ohms, and 75 ohms inductive reactance. So this one's going to be inductive. And since we're going to wind up with what, 50 ohms reactance and 100 ohms on the real axis, it's going to be a low angle. So 27 degrees.
Our tangent of 50.
Yeah. Okay, more of this susceptance and admittance stuff. So we talked about admittance, which is the inverse of impedance. We use Y. So Y is equal to 1 over Z, or Z is equal to 1 over Y. And they measure it in Siemens. I forgot when they changed that. It used to be nice because they did all this stuff in modes, which was ohm spelled backwards, and they used the capital omega upside down. I thought that was neat, but then somebody came up with the Siemens bit. There's a guy named Siemens that did something.
Made a lot of money in Germany.
Huh?
I made a lot of money in Germany.
Strange.
So the susceptance is the equivalent to reactance. So it's the reciprocal or inverse of reactance. So I don't have a good definition for it, but it's just basically 1 over X. And they use B to represent it. So here's the relationships of all of them. If you convert to polar form, as opposed to rectangular coordinates, where you get impedance at a vector magnitude at an angle, like we were doing with the arctangent. In order to convert to admittance, you take the reciprocal of that impedance vector and you change the sign of the angle. So if it was a positive angle, it becomes negative, and the length of the vector is the reciprocal of it. what is admittance? Alpha. So I like to think admittance admits, impedance impedes, conductance conducts, resistance resists. How is impedance in polar form converted to an equivalent admittance? Doing throwaways, Charlie and Delta. What is susceptance?
Charlie.
What letters commonly used to represent susceptance? What's the effect on the magnitude of a pure reactance when it is converted to susceptance?
D.
Becomes a reciprocal. Okay, so we learned about series of parallel circuits, RMS, power, peak envelope power, decibels, time constants. Basically, remember that one time constant is approximately 5/8. 5/8 would be 62.5. It's close enough for approximations. And 3 time constants get you 95%. And you never actually get to 100 in theory. And Eli the Iceman. And then all this resistance, reactance, impedance, conductance, susceptance, admittance, and how to convert the polar forms. But I need a pee break.